What is EMR or electromagnetic radiation? I will help you. Electromagnetic radiation is defined as oscillating electric and magnetic field perpendicular to each other and perpendicular to the direction of propagation. So it consists of oscillating electric field, and perpendicular to that there is a magnetic field. They are mutually perpendicular and perpendicular to the direction of propagation. For convenience, we are dividing the electromagnetic radiation to different regions from very low energy to very high energy. I'm going to clean the board. We will see the different regions and associated type of spectra very briefly. The different regions, I have told you that first one is radio wave. For convenience, we are dividing the entire electromagnetic radiation to radio waves, microwaves, infrared, visible, ultraviolet, X-rays and gamma rays. For convenience, once again, the infrared and ultraviolet are again divided. Let us see what are they. Radio waves. What will be the wavelength? How will you represent the wavelength? Wavelength can be represented as lambda. The radio waves are having wavelength is equal to 1000 nanometer. And we can see it is having wave number. Wave number is equal to what? 1 by wavelength. It's called wave number. Wave number is equal to 0.01 inverse centimeter. It is customary to express the energy in spectroscopy in terms of wave number. Wave number is used in the unit centimeter raised to -1 in spectroscopy. Because the fundamental energy unit E is equal to h nu, h c by lambda is equal to h c nu bar. Where nu bar is the wave number, c is the velocity of light, h is the Planck constant, lambda is the wavelength. So energy is directly proportional to frequency. Energy is inversely proportional to wavelength. Energy is directly proportional to wave number. In spectroscopy, we are using wave number. So second level is microwave. Microwave region. Microwave region. See, in radio wave, 1000 nanometer or nanometer means what? 10 raised to -9 meter is called a nanometer. Or 0.01 centimeter raised to -1 is used. So it is responsible for the nuclear magnetic resonance spectrum. So interaction of radio wave with the molecule, organic molecule will give nuclear magnetic resonance spectra. It's a very valuable tool for organic chemistry, especially for the determinant of structure and all other properties. Even the presence of isotope can be determined using nuclear magnetic resonance. This is very similar to the MRI scanning in medical diagnosis. Second type of region of electromagnetic radiation is microwave, that is of 100 nanometer. And the wave number you can predict will be equal to 0.1 centimeter raised to -1. And in this region, there are two possibilities. One is ESR. ESR means electron spin resonance spectra. We should understand that electron spin resonance requires, that is, change of electronic spin requires 1000 times the energy than nuclear magnetic resonance, that is, change in the nuclear spin or resonance in the nuclear spin, that is proton and neutron. So microwave region will give two types of spectra. One is electron spin resonance spectra. Second one is the conventional rotational spectra. If the molecule is having permanent dipole moment, it will give rotational spectra. Example is water. Is a molecule having permanent dipole moment. Meanwhile, I'll tell you that the rotational excitation of water molecule in the food sample and the transfer of energy to other molecule is responsible for the or the basis of microwave cooking. Microwave cooking is possible by the transfer of energy from the rotational energy from the water molecule to the rotational energy of water molecule present the food material to other molecule. I will repeat, the rotational excitation of water molecule in food and the transfer of the energy to other molecule is the basis of microwave cooking. Now, next region is infrared region. Infrared region, in the coming classes, we will say that it is suitable to divide into far infrared, mid infrared, and near infrared region. The far infrared region is of the order of 10 inverse centimeter, and mid infrared is of the order of 200 inverse centimeter. Near infrared is of the order of 4,000 inverse centimeter. It's not the wavelength, it is the wave number I am explaining. Because in spectroscopy, we are interested that all this will give the rotation and the vibration. Along with the vibration, simultaneously there will be rotation. Rotational vibration spectrum is there, which is called the infrared spectrum. Infrared spectrum is called rotational vibration spectrum. Using this spectrum, rotational vibration spectrum, we have seen that we can determine what are factors. Using rotation vibration spectrum will give the force constant, frequency, and even the dissociation energy can be calculated using the rotation vibration spectrum. The force constant will give valuable information like bonding, single bond, double bond, triple bond, etc. Next comes the visible region. Visible region is possible in between the region 780 nanometer. Starts from the 780 nanometer and it is having the value of 12.8 times 10 raised to 3 inverse centimeter, or 1.28 times 10 raised to 4 inverse centimeter. This is called a here the electronic spectrum is possible. Electronic spectra will give the stability of the molecule. If it's a weakly bonded molecule, it will easily dissociate the stability of the molecule. Electronic spectra also will give the electronic state of the molecule. Where the electronic state, what about the outermost electron, whether they are exciting to the higher level or coming back to the penultimate orbital, etc., can be predicted in the electronic spectra. We'll see later in the details. Next comes the ultraviolet spectra, UV spectra. UV spectra also divided into two. They are the near UV, near ultraviolet, that is of the order of 380 nanometer. 380 nanometer is equal to 26.3 times 10 raised to 3 inverse centimeter. Because the 10 raised to 3 factor we require. That is why I am writing, instead of 2.63 times 10 raised to 4 inverse centimeter, I am writing 26.3 times 10 raised to 3 inverse centimeter. And then comes the vacuum ultraviolet. It is called vacuum ultraviolet because in order to evacuate the tube, in order to study the spectrum, it is possible to study the spectrum only in the vacuum. So it is called vacuum ultraviolet. Vacuum ultraviolet is starting from 200 nanometer wavelength, 200 nanometer wavelength to 50. That is called 50 times 10 raised to 3 inverse centimeter wave number. So vacuum ultraviolet and near ultraviolet regions are suitable for the study of ultraviolet photoelectron spectra. Ultraviolet photoelectron spectra, called UPS shortly. Ultraviolet photoelectron spectra is possible in this region. Next comes the ESR spectra. Next comes the region called after ultraviolet. In the region of electromagnetic spectra, we have X-rays and gamma rays. Next comes the X-rays. X-rays are starting from the 10 nanometer. 10 nanometer wavelength, that is of the order of 10 raised to 6 inverse centimeter. Very powerful. And in this region, we will study X-ray photoelectron spectra, called XPS. XPS is X-ray photoelectron spectra. X-ray is starting from 10 nanometer wavelength or 10 raised to 6 inverse centimeter, in which X-ray photoelectron spectra we are studying. Next region, higher region, is gamma rays. In gamma ray region, that is starting from 10 picometer or picometer, 10 picometer, and it's having wave number 10 raised to 9. 10 raised to 9 inverse centimeter wave number. In this Molecular spectra, which will give the interaction of gamma rays with the molecule, very valuable spectra, is called a Molecular spectra. We will study. This is the introduction of what are the different regions and resulting spectra. So, notable important merit of molecular spectroscopy as an analytical tool will be this one. Please listen. Following is the very important or notable merit of molecular spectroscopy as an analytical tool. There are important 4 points to be remembered. That is, first one is only very small quantity of the substance is required. It may range from 2 milligram to 5 milligram is enough. But if the conventional laboratory method, routine analytical method, requires 1 gram or above of the sample. Here only 2 milligram of the sample is sufficient. The first point is few milligram of the sample is required. First point I will write as few milligram. Few milligram of the sample is required. Second point is there is no destruction of matter, destruction of molecule. But there is another molecular spectroscopic technique called mass spectrum. I haven't mentioned here, where that analytical tool will dissociate a molecule to fragments and study. Except a mass spectra, there is no destruction. The molecule will be intact. There is no destruction of matter. That means after the study, the sample can be used again and again. There is no physical or chemical change due to the study. This is just like taking the MRI scanning of our head. After MRI scanning, we need not submit the head to the laboratory. We can take it back. Okay, there is no destruction. In all the conventional routine laboratory method, what we are doing, we are mixing with the chemicals and pouring in the sink, wasting the chemicals. So one is a unique merit is there is no destruction of the matter or the molecule after the study, during the study. Okay. Third important point is that analysis will take only few seconds to few minutes. The maximum few minutes only is sufficient. Few minutes. In routine laboratory, We'll take 1 or 2 hours and we'll arrive at some vague conclusion that this organic compound, this is saturated organic compound having aldehyde group, etc., or ketonic group, etc., or unsaturated compound, etc., never mentioning what exactly is that compound, and wasting about 1 and 2 hours, wasting a lot of chemicals. Okay, so few minutes only we are taking to analyze using spectroscopy. The fourth very important thing is the structure information that is obtained from the molecular spectral study, like the structural information like a bond length, bond angle, force constant, dissociation energy, then stereochemistry, etc., are very dependable, and there is slight error. Error is almost negligible. And we are depending, even now we are depending on the internuclear distance of hydrogen chloride based on the rotation spectra study. So very important thing is dependable, no error possibility in the determination. Error is very, very less or negligible. All this depends upon the fundamental equation I have mentioned already. What is the fundamental equation? Energy is equal to h nu, energy is equal to hc by lambda, energy is equal to hc nu bar. And nu bar is the thing that we are going to use always. In the spectroscopic study, the fundamental technique is using the very pure sample, we will have a spectrum. There is a similarity. Suppose your right finger, thumb you are using, the fingerprint you are using. What's the nature of your fingerprint? What's the unique character of your fingerprint? Nobody in the universe who are died, who are living, or who yet to be born will have that fingerprint of your thumb as you. That's unique one. Similarly, the spectrum of a particular organic compound, particular inorganic compound, but even water, pure water, will be unique. See, suppose there is a tritium or deuterium present in water, then the spectrum will have that particular point, particular presence of isotope clearly mentioned. As an example, I will draw the spectrum of rotation spectrum of hydrogen chloride gas. See the spectrum of hydrogen chloride gas. I'm going to clean this board. See the hydrogen chloride spectrum. The usual hydrogen chloride rotation spectrum will be of this nature. The usual hydrogen chloride spectrum will be, this is the nature of hydrogen chloride spectrum. The spectrum will be first increasing. The peak will be first increasing. The peaks are first increasing and then decreasing. This is due to the population distribution that we will study later. This is pure hydrogen chloride, HCl 35. HCl35. If you are taking pure hydrogen chloride, this will be a spectrum. What is this? The x-axis will be the force constant, the rotation constant B versus the frequency, inverse centimeter. Okay, this will be the nature of the spectrum. See, if the spectrum hydrogen chloride is mixed with HCl35 along with HCl37, the spectrum will be having some difference. Please note what is the difference you are seeing. Something on the side. There is a splitting on the side. And this splitting is due to the presence of HCl37. If HCl35 is mixed with HCl37, this will be the nature of the spectrum, which shows that in the universe, 25% is the natural hydrogen chloride gas, natural. In this universe, 25% will be HCl37 and 75% will be Cl35. So that information, isotope presence even can be determined using spectrum. With this introduction, we'll stop at present. We'll continue later.